Hello everybody. Today I want to share a different understanding of the Monty Hall problem. I have watched several videos talking about it. The first one was Harvard 110 Stats Introduction to Probability course. It was on lecture around 6 or 7. There's 3 ways. He talked about branching tree diagram, law of total probability, Bayes rule. And I think he solved by 2 ways. The first was a tree diagram and the second was law of total probability. So first of all, I want to introduce the rule or the game, because as long as you have studied this probability, maybe you have heard about this problem in the past through readings or movies. The Monty Hall is the host of game. There's 3 doors. Behind each door, there's either a goat or a car. 2 of 3 doors has a goat, and 1 out of 3 doors has a car behind it. Everybody, we assume that our objective is to get a car. Of course, the host asks you to pick a door. Firstly, they will not open the door to reveal the result immediately. Actually, the host will open a door to show you a goat. He knows the goat and the car behind each door. He knows exactly the information behind the doors. So that's the assumption. Monty Hall always open a goat door after your initial pick. And then he'll ask you, would you like to switch or stay with the original pick? First, you chose the door with the goat, and he opens the door with the goat. In this case, he doesn't have a choice. He had to open that door that has a goat because you picked the goat door. And there's only 3 doors. 2 of them have a goat, and one of the door has a car. So that's how it plays. So we assumed if he has a choice, he picks with the equal probabilities. It means that your initial pick has to be a car. So that was an important assumption, I believe. All right. So this is initial pick. At this stage, we don't know if it has a goat or it has a car behind. And then Monty Hall, let's say, opens the door number 2. It has a goat. What happens on the stage 2 is that you get to switch to number 3, and it can be opened. So what opened after the game ends is 2 doors. 2 doors can be open. Your initial pick, and you choose to switch. At the final stage, 2 of the door out of 3 doors were opened. If you don't want to switch, of course, after the game, it's for the television, for the show, all the doors open at the same time. That's actually a confusing point. If you choose to not switch, you're dedicated with this 1 door, which was 1 out of 3 door. So instead of doing the game like this, we could say that initially there's only 1 stage. Let's say I say this is another game. You're given an option of choosing 2 doors. Choosing 2 doors, always you can choose 2 doors. 1, 2, 3. So all the outcome is gonna be you choose 1, 2, you choose 1, 3, or you choose 2, 3. So those are the outcomes. And let's assume that the car is behind the door number 1. This outcome and this outcome forms 2 out of 3 outcomes that has a car behind the door number 1. We assume 2 outcomes has a car behind door number 2, and 2 outcomes has a car behind the door number 3. If you were given chance of choosing 2 doors out of 3 doors, the probability of getting a car is always going to be 2/3. That's the key point of my understanding here. It is always certainly going to be higher than the picking 1 door and reveal immediately. So because picking only giving you option of 1 door and 1 chance, the outcome is gonna be 1, 2, and 3, right? You can choose 1 to 3. if the car is behind one of them, the probability of getting car is always going to be 1/3, no matter which door you choose. Situation is equivalent to always switch, and this case equivalent to always not switch, which is the 1/3. For the completeness, I don't think I can. Okay, let's do it. For the completeness, I would like to present here one of the way called tree diagram. And to define the branching, think like a mathematicians or someone who studied the first few lectures of probability. This is how we're going to approach this problem. We assume that we pick 1, so that the knot start from here. We pick the door number 1. There will be 3 knots. This is the first level. I think it's better to do like this. Yeah. The first level is we select a door. So second level of branching is car door. Well, everything from here is from the lecture of Harvard Stats 110. And here I just want to present the easier way, tree diagram. So the second level was car door. This door number 1, door number 2, this door number 3. So the car behind door number 1, 1/3 of the chance. Behind door number 2, 1/3 of the chance. Behind the number 3 is also 1/3 of the chance. Monty Hall chose a door, so it's called Monty door. Monty door, do you remember that we talked about whether he has an option to choose 2 doors, to pick 2 doors with equal probabilities, or he has to pick the one with the goat? Right here, we have to already assume that the car is behind the door 1. So if the car is behind the door number 1 and we pick the number 1, Monty has options in this case to mark that the door is behind the number 1. The third level knot can be produced given that the car is behind door number 1. Now Monty can choose equally door number 2 or door number 3 to open. So this is 1/2, same probability. Now here, if the car is behind the door number 2 and the initial pick was door number 1, now the Monty can only choose door number 3 because door number 2 has a car behind. When he doesn't have a chance, he's 100% going to open the door number 3. The probability of open door number 3 is 1. And if you choose door number 1, the car is behind the door number 3, he will definitely open the door number 2 with the probability of 1. What's next? Should we switch, right? So if you choose the door number 1 initially, and the Monty sometimes can open door number 3, sometimes can open door number 2. And in those 2 cases, if you switch from door number 1 to door number 2 or door number 1 to door number 3, you get the car. But in this case, if you switch from door number 1 to door number 3, or if you switch from door number 1 to door number 2, you don't get the car. The car was behind door number 1. On the same line, we have to use this number times this number. It is 1/3 times 1/2, and plus the other situation. And the entire thing is the probability of not getting the car. So we use the law of complement. We use 1 minus this probability. We get the 1 minus 1/3 is 2 out of 3. So that's the tree diagram. For completeness, another way is the law of total probability. We wish we know where the car is. The lecture defined 2 events. Event capital S succeed, assuming always switch. The event D sub j is defined as door J has a car. J could be 1, 2, 3. Something the lecturer didn't say, but I would like to add that the law of total probability has some assumptions. If anyone studied it, could remember that something like this was formed. Those are 3 blocks fully covers the entire set, the whole thing, and they are not intersect with each other, and there's a smaller set in the whole set and intersect with each of the event. In order to know the gray area, we use the event inside and the event of this each the intersect area. We basically add all the intersect area. To be clear, we could call this D1, D2, and D3. And in this case, succeed assuming always switch is the gray area. And what is the non-gray area? So those parts. Those parts is going to be, I guess, fail or succeed, but always not switch. Maybe. I'm not sure, actually. Sorry for the unsureness. But let's keep going. So the P of S is equal to... Because for conditional probability, there is a whole set and there's A and B. And this gray area is actually denoted as probability of A given B. Probability of A given B was defined as you could see according to the Venn diagram, the probability of A intersects B over the probability of B. Is that right? Yeah. Because the probability of A intersects B is this area. And the probability of B is the B, right? Yeah, and to be clear that the probability, because this area is actually inside the big entire set, and this area is also inside the entire set. If we were writing like so, we basically, it's a ratio, right? So because this is also a ratio, this is also a ratio, this is also a ratio, area of this circle over the area of the square, and this is the area over the area of gray area over the square. So the square was canceled out. That's how we got I got this result. That's how we got this. From this, we can get P. A probability of A intersect B is going to be probability of A given B times probability of B. So this is a key definition. So now, why we can use the law of total probability is because it satisfies the assumption of the law of total probability. So now we can use it. The probability of succeed, assuming always switch, is P of S, is going to be equal to the P of S intersects with D1 plus P of S intersects with D2 plus P probability of S intersects with the D3, and which is going to be equal to P of S given D1 times P of D1 and plus P of S given D2 times P of D2 plus P of S given D3 times P of D3. And this needs brain work to have those notations converted to numbers that we actually know according to the rule of the game. So what is the probability of of succeed, assume always switch given door number 1 has a car. So the door number 1 has a car, we can come back. The probability to always switch, right? If we initial pick was 1 and the door number 1 has a car, and we switch to door number 3 or door number 2, as we calculated was this number. Was it this number? Yeah. So we got is 1/3. So this is 1/3. Wait. The probability to succeed, assuming always a switch, is 0. Because we're not going to succeed if we're not going to succeed. This is not going to succeed, so yeah, it's 0. And the probability of a car behind door number 1 is 1/3. All those are 1/3. All those. Because there's no condition, it's just a probability of door 1 or has a car, or door 2 has a car. There's equal chance of having a car behind, right? Door 1 has a car, or door 2 has a car, or door 3 has a car. This 3 forms an entire set. There's no more doors, and there's only 1 car. So yeah. And we just figured that there's no way of succeed given that door 1 has a car. We always switch, assuming, and that we get succeed given initial pick was door number 1. And in this case, we always switch. We could definitely succeed, right? The probability of succeed given door 2 has a car. We come back to the tree diagram, because in this case, in this tree, which we picked 1, we picked the door number 1. And now you're saying that door 2 has a car. So the car is behind door 2. Monty Hall opened the door 3 because he's not going to open the door 2 because it has a car. So we switch from door 1 to door 2, we succeed, assuming switch. Yeah, we switched and we succeed. The chance is 1, same as this case. So we multiply them together and add them together. The first number is 0, second number is 1/3, third number is 1/3. So the final chance is 2 out of 3. 2/3 chance we succeed, assuming always switch. That makes sense. All those area that's not gray, it can only represent that we fail, because we can't succeed. Yeah, there's a one thing. We succeed, but we don't switch. And I don't know where we fail. Which part represents we fail? We could fail and we don't switch. And we could fail, switch. Yeah. But those are not the most important part in this presentation. The last method is Bayes rule. I will leave it here. I probably need to get my thoughts right. And the one thing left I forgot to talk about was here. My method that I wanted to share was this. Initially, you were given 2 doors to choose and end the game. To list all the possible outcomes is one way, and the other way is you choose 2 doors, right? Well, my friend told me that you choose the first door out of 3. You get 1/3 of the chance of getting the car, but you were given 2. You were given 2 doors to open. So first you open this door,
you get the 1/3 of chance of getting the car, and later you get another, immediately after that, you get another chance of opening a door that only open one out of two doors. So you get 1/2 the chance getting a car. And so if you were given chance of opening two doors at a time, and in the game you get this total probability is 6, 2 plus 3 is 5 out of 6. That doesn't look right. So this, let me check, this is wrong. So we can't think like this. All right, I'll leave it here. Sorry for the confusion, but this is not right. Anyways, so thanks you guys for watching. Well, I would like to see your ideas. If you have any, please leave comment, like the video.